Let's talk about the normal distribution. This is the formula for the normal curve, and this is its graph. In this lesson, we are going to derive this formula, and we are going to do some simulation to better understand the concept of normal distribution, which is very important in our next lesson on the central limit theorem, which forms as the backbone of many hypothesis testing that we are studying in inferential statistics. So let's begin with our simulation. What I have here is a Plinko probability simulation from the University of Colorado PhET project. In this simulation, I'm going to drop some marbles, and we are going to see where the marble would settle down. Let's say I drop 10 marbles, and many of those marbles settled at the middle. Let's drop 100 marbles. Notice that we now have this distribution where many of the marbles are lumped together somewhere at the middle of the distribution. And we can look at the corresponding histogram. Now, if we increase the number of marbles and we speed up the simulation, after about 2,000 marbles, we now arrive at this distribution. The ideal mean is a mean of 6. And the sample mean that we got is 5.993 out of 2,033 marbles. The ideal standard deviation is about 1.732, but our sample standard deviation is a little less than that at 1.661. If we superimpose the ideal, which is the blue histogram, over the sample histogram, which are the red bars, we now have this red distribution that is almost similar to the ideal distribution. And if we increase the number of marbles to, let's say, 10,000, 100,000, or 1 million, this sample distribution would be almost similar to the population distribution. And this kind of curve that looks like a bell-shaped curve is what we call as the normal curve. And in this lesson, we are interested in getting what is the equation of this curve. For our derivation, let's begin with our idea of what a normal distribution is. We say that data are said to be normally distributed if the rate at which the frequency fall off is proportional to the distance of the scores from the mean and to the frequencies themselves. So let's say this is our normal curve, and the x-scores are scores that are distributed along the horizontal axis, and the frequency of the score is represented by the height of the curve. For example, for this particular x value, let's say x of 1, there is a corresponding frequency, and that frequency is denoted by our y value, y sub 1. Notice that as the distance of the x value becomes farther away from the middle, which is our mean, the height of the curve is also lesser. And if the distance is closer to the mean, then the height of the curve is taller. And so if we want to get the rate of which the frequency fall off with respect to the distance of the score from the mean, then we can come up with this ordinary differential equation. The rate of change is represented as dy over dx, where y is the equation of our curve, is equal to the product of the distance of the score from the mean times the height, which is represented by our function y, times certain constant. And our curve is concave downward, as represented by this negative sign. So in here, our k is a positive constant, so negative k therefore is a negative number. Let's focus now our attention to this differential equation. What can we do to solve this equation for y? First, we can use the concept which we call as separation of variables. In the separation of the variables, our goal is to gather all the x variables in one side and the y variable at the other side of the equation. So we now arrive at this form. We multiply both sides by dx and divide both sides by y to arrive at dy over y equals negative k times the quantity x minus the mu times dx. Here, the mu is the population mean, and the x is specific x scores. And then to simplify this equation, let us integrate. So integrating both sides, we now arrive at the indefinite integral of dy over y, which is ln y plus some constant, and the antiderivative of the right side, which is equal to the constant times the antiderivative of the quantity x minus mu, which we can compute by applying the power rule of integration. And so we arrive at this expression at the right plus some constant b. Now, if we subtract both sides by a, since a and b are constants, the result is just another constant. And let's call that difference between b and a as a constant c. So our general form now is ln(y) is equal to negative k times the quantity x minus the mu squared over 2 plus some constant. Then in order to simplify this, we can take the exponentials of both sides. And so we now arrive at the natural number e raised to ln(y) is equal to the natural number e raised to this expression at the right side of the equation. And then applying law of exponent, we arrive at this expression. Now, since e raised to some constant is just another constant, we can now let e raised to small c be equal to capital letter C, and by commutative property, we now arrive at this equation for our normal curve. Now, since we want to have a probability distribution, the area under the curve must be forced to be equal to 1, because probability is between 0 and 1. And in order to force the area under the normal curve to be equal to 1, we need to find some constant to make that happen. But unfortunately, this integral does not have an elementary function as its integral. But we can apply some trick, and the trick is like this. To find the definite integral of the equation of our normal curve from negative infinity to positive infinity, and let that value be equal to 1, we perform what we call as the u substitution. So we let u squared be equal to this exponent k over 2 times the quantity x minus mu raised to the second power. Notice that we did not include the negative sign. That is because we want to get u. We want to get the square root of both sides to find the value of u. And so we now arrive at u equals the square root of k over 2 times the quantity x minus mu. This is a valid operation because remember at the start, we let k be a positive number. So we are not getting an imaginary value here. And since u now is equal to that expression, we can now compute for its derivative. The derivative of u with respect to x, du over dx, is equal to the constant square root of k over 2 times the derivative of x minus mu, which is equal to 1. Take note that k is a constant. And so du can now be expressed as the square root of k over 2 times dx. And multiplying both sides of the equation by the reciprocal of the square root of k over 2, we arrive at dx equals the square root of 2 over k times du. We need this expression in our u substitution. So remember this value. So this is the area that we want to be equal to 1. And using the c substitution, now here, since our dx is equal to the square root of 2 over k du, we can now put this du here and this square root of 2 over k as a factor outside the integral symbol, and we just copy the c. And notice that this part is equal to our u raised to the second power, u squared. And so we just copy this e, copy the negative sign, and our exponent now becomes u squared. So these two expressions are equal, and we want its area to be equal to 1. So let's focus now on this part of the equation. Now this kind of integral is also called Gaussian integral, named after Carl Gauss. And the technique to simplify this is to square the integral. But we are going to use some theorem, which we call as the Fubini's theorem. So let's first square this integral. So square the left side and square the right side. And then squaring this integral would result to a double integral, which is now in the form like this. We square the c to get c squared. We square the square root of 2 over k to get 2 over k. And then squaring this resulted to this double integral, and we replace the exponent negative u squared with negative quantity x squared plus y squared. And since we are multiplying two integrals, we now have here two differentials equals 1. Let me explain this last part. To understand that, let's say we have this I, which is equal to the integral of e raised to negative x squared dx from negative infinity to positive infinity. This integral is also equal to another integral of the same form, even if the variables are different, because the variables here are just dummy variables. It doesn't matter whether you use x, y, z, or any variable, as long as the form is the integral of e raised to negative of certain variable squared d of that variable, you will get equal integrals. And if you want to square I, it's just the same as multiplying I times itself, but each of these are equal to I. So we can also get the product of these two integrals. And using the Fubini's theorem, we can now compute double integral using an iterated integral. And this is what we mean by an iterated integral. You have two integrals. One is inside another integral. The yellow part is inside the white integral. And applying the law of exponent, we can now simplify this inside part as e raised to negative of the sum of the exponents, x squared plus y squared. All the rest are just copied. We want this to be in this form because our next step is we want to change coordinates from Cartesian coordinate system to the polar coordinate system. And this x squared plus y squared can be replaced by r, or the radius, in the polar coordinate system. And so let's now rewrite the integral into the polar coordinate system. So from the Cartesian form to the polar form. Notice that here, we just copy the constant, we copy the e, we replace x squared plus y squared by r squared, and we replace dx dy by r dr d theta, and the limits of integration from negative infinity to positive infinity to 0 to 2 pi, and the limit of integration for our dx from negative infinity to positive infinity now becomes 0 to infinity in our dr differential. Why is that so? If we're going to recall our polar coordinate system, the coordinate x is replaced by r cosine of theta, and the y coordinate is replaced by r sine of theta, and our radius squared is equal to x squared plus y squared, applying the Pythagorean theorem. And when we have double integral like this dA can be interpreted as a small rectangle, which is the product of the change in the radius times the change in the angle. Now, let's say this small sector is our dA. This sector can be computed by getting the difference between the length of the radius, which is delta r, and the change in the angle times the radius, which is r delta theta. If our change in r becomes very, very small or infinitesimal, this delta r becomes dr, and this delta theta becomes d theta. And so, the area now, which is our dA, becomes the product of this dr times r d theta. Technically, the shape of this sector is not a rectangle. This is a sector of a washer or a sector of a disk. But as d theta and dr becomes very, very small, then the shape can be approximated by a rectangle. And so the product of the length and the width becomes the area. That is now the explanation why dx dy is now replaced by r dr d theta. And so at this point, we now have this integral in the polar coordinate system. And this is something that we know how to integrate. So let u be equal to r squared. It follows therefore that du over dr is equal to 2r, and r dr is equal to 1/2 du. We are interested in finding the value of r dr, so we can replace this value by whatever is this value. So using now u substitution again, this integral at the top can now be replaced by this integral at the bottom, where e raised to negative r squared r dr d theta is now replaced with e raised to negative u du d theta. Because r dr is equal to 1/2 du, we factor out the 1/2, so you have the 1/2 here outside. But since we have here a negative sign, then our constant is negative 1/2. All the rest are just copied. But notice that there is a change in our limits of integration. The reason behind that is when we switch to the polar coordinate system, if we have this point xy in the Cartesian plane, in the polar coordinate system, we now represent this point as an ordered pair of an angle and a radius r. And our radius is from 0 to positive infinity, and our angle is from 0 angle, and we rotate up to 2 pi. That is the reason why for the radius, our limit of integration is from 0 to infinity, but for the angle, our limits of integration is from 0 angle up to 2 pi, which is one complete rotation around this circle. And again, we want to find the value of c here so that the area is equal to 1. So let's simplify now this integral. The integral of e raised to negative u is equal to e raised to negative u plus c. We do not write the constant anymore because when we perform definite integration, we'll just cancel out that c. And so evaluating now e raised to negative u from 0 to positive infinity, so we now have here e raised to negative infinity minus e raised to 0. But e raised to negative infinity is approaching 0, and any number raised to 0 is 1. So what we have is 0 minus 1 equals negative 1. And therefore, we can now replace this part by this negative 1. All the rest are just copied. And then we can put this outside. So negative 1 times this negative becomes positive. And we now have the integral from 0 to 2 pi of d theta, which is just equal to 2 pi. So this part here is equal to 2 pi. All the rest are just copied. And then solving now for c, we have c squared is equal to k over 2 pi. And finally, c is equal to plus or minus the square root of k over 2 pi. But we want the area to be positive 1. So we just take the positive value of the constant. Since the constant is equal to the square root of k over 2 pi, then the equation now of our normal curve is now given by this equation. The original equation that we arrived at, replace c by this constant, and so we now arrive at our equation for the normal distribution. Let's inspect this equation. Notice this part here. This is the distance of any x-score from the mean. If we want to convert this into the standard normal score, z equals x minus the mean over the standard deviation, we can adjust this k so that we can arrive at a form x minus mu over the standard deviation here. And if we adjust this value of k, then there is a corresponding change also in the value of k here. Let's do that. If we let k be equal to 1 over sigma squared, which is the variance, we now arrive at this equation. Instead of k, we replace it by 1 over sigma squared. Instead of this k, we replace it by 1 over sigma squared. And simplifying further, we can simplify the square root of 1 over sigma squared as 1 over sigma, then copy the rest. We can also write this as one term, that is the quantity x minus mu over sigma all raised to the second power. And finally, we now have this equation for our normal curve, which is the equation that we started with in our introduction. So let's go to Desmos graphing calculator and see how the graph of this equation look like. So what you can see here now is the equation of the normal curve where the sigma is given a value of 1 and the mu is given a value of 0. Let's look at the graph. So this blue graph is the graph of the normal curve with a standard deviation of 1 and a mean of 0. That means we center the graph at 0. This is the standard normal distribution. All the other curves are still normal curves. For example, if instead of 1, our sigma is 2, so we replace sigma by 2, and our mu is 5, look at the graph. This purple graph is still a normal curve, but this blue graph is the standard normal curve. The standard normal curve happens when the mean is 0 and the standard deviation is 1. If we have another equation here, the standard deviation is 0.5 and the mean is at -3, we now have this black graph. Is there any pattern that we can observe? We notice that when we change the mean, we translate the graph of the standard normal curve to the left or to the right, depending on the value of the mean. If the mean is positive, we go to the right. If the mean is negative, we go to the left. If we change the sigma value or the standard deviation, if the standard deviation is bigger, as in this purple curve, notice that the distribution is more spread out. When the standard deviation is smaller than 1, the distribution is more compact. Most of the data are distributed around the middle of the graph. Now, it's not easy to compute for the area of any normal curve. That's the reason why we tried to convert any normal curve to the standard normal curve by applying the z-score. The z-score is equal to x minus the mean over the standard deviation. This formula is designed to convert this purple curve to have a distribution similar to this blue curve or this black curve, so that its distribution is converted to this blue standard normal distribution. And we are doing that because we want to use the z-score table at the back of our statistics book. By doing so, we do not need to compute for the integrals. All we have to do is use the table, because computing for the area under the normal curve is not an easy task. So thank you very much, and we hope to see you again in our next video.